Thanks, Mr. Pradisha, and firstly, thanks for this opportunity as well to talk. To talk about something which I had worked on almost 17 years ago, but I think which is still relevant in some sense. And so, firstly, let me give you a quick introduction to myself, and let me try and understand the audience as well. Right? So, I understand that most of you are, senior undergrad or graduate level CS people. Can I assume some kind of CS background from? So, let's say automata theory and formal languages. We'll study them, but I'll try to move through them as quickly as possible. Right? Anyone here who is a working professional who is working on workflow design or systems design, systems analysis? There is some. Okay, great. But mostly fresh audience. That is mostly students. Is that what? Okay. Okay, so my tutorial talk is on the problem of what we call open world computing. Right, and I don't have specific slides as such. I have a set of slides from different talks and courses that I've given, so I'll just use them off and on as required, right? And but for most of the course, next 3 lectures, let's keep it as extempore as possible and as interactive as possible, right? And so at any time, if you feel any doubt, just stop and ask me a question. So let's try and keep it as interactive. Right? Let's also try and make it more practical, in the sense, let's try and solve some problems as we go along to try to get our understanding of what open world problem. So what is open world computing? Mostly you have talked about algorithm design, right? You have studied algorithms, data structures, right? How do you write an algorithm for sorting? How do you write an algorithm for searching? Finding the max of something, finding prime number, all kinds of algorithms you have written, right? And of course, you have also studied the theory of algorithms. I guess you have already studied how to analyze algorithms, the big O notation, the theta notation, the asymptotic complexity, right? And complexity classes, NP hard, NP complete, and so on. Okay. Have you also studied about computability and uncomputability of problems? Is it making sense, or if I say an uncomputable problem, have you already studied that, or not yet? Okay, so let's do that as part of this. Okay, and have you studied Turing machines already? No. How many of you have a formal introduction to Turing machines already? Okay, quite a few, but quite a few are not there. Okay, so let's get a good introduction to the theory of classical theory of computing as well, right? And are basically what I would call the classical algorithms. Okay, theory of underlying algorithms and stored program computing. Okay, which is what is represented by the mathematical model of Turing machines. But the thing is, in practice, okay, this is the reason why I was talking about are there any people who are involved in application design? Okay, so in practice, we don't necessarily design algorithms. Okay, in fact, you probably use an algorithm from some library and so on. Instead, what is it that you design? What is the major challenge that you encounter? You design what are called systems, right? You don't, you don't spend your, you don't get your salary if you just write an algorithm. Right? You have to build a system. You have to build a, payroll management system. You have to build a banking system. You have to build some kind of system, right? And so this whole tutorial here is to try and understand the difference between systems design and algorithm design, right? And systems design, we will argue, is primarily what is called as an open world problem, right? Systems, while in a lot of algorithm design, we model it like a closed world computation. So I'll clarify what these terms mean in a while, okay, as we go along. But have you all got the idea what is the primary objective of this part of the work is about? The mathematical foundations underlying systems design. Okay, by systems design, what do we mean? We want to create a workflow. We want to create a applications program. We want to create several different instances of workflow working together. What is the main problem with all this? Okay, the main problem with all this is that systems work in an environment which is open-ended, right? That is, what do we mean by open-ended? Let me give you a quick exercise. Okay, make a list of 5 things that you don't know. Can you quickly make a list of 5 things that you don't know? So let's try and understand what open-ended means or open world means. Can you make a list of 5 things that you don't know? You're all blank. Why? Because we don't know what we don't know, right? I mean, if I say I don't know calculus, that means you know that you don't know calculus, right? So if you have made 5 things, then I would have said, okay, you know that you don't know these 5 things, right? But there are so many things that you don't even know that you don't even know, right? So we don't know what we don't know, right? That is really the open world problem, right? So every system, okay, has to operate in an environment that is open, okay, in the sense that anything can happen and we don't even know what can happen. Okay, so think of a problem like this. Okay, let us say you want to drive home from work. Okay, so what are the challenges you can encounter? Okay, so you will encounter traffic, of course. Okay, some congestion, maybe rain, potholes. Will you encounter an elephant going on the street? Maybe, yeah. Why not? It's possible, right? Will you encounter an earthquake? Yeah, why not? Okay, or will you encounter a dinosaur coming back to life while going? Yeah, all those challenges are possible, right? And so this is what is the open world problem. That is, when we design systems, they have to work in an open world. Okay, open-ended world, and we don't know what will happen in the open-ended world. Okay, and we don't even know what we don't even know, right? And so that's the problem. Okay, so I hope I've sufficiently excited all of you, okay, in terms of the problem statement that this is the major challenge that we are looking at. Okay, so this problem had or this idea of open world computing had created a lot of interest in the late 90s and early 2000s. That's when I got my PhD. So at that time, AI, artificial intelligence, was going through a trough. So there were expert systems and all kinds of other in the 70s and 80s, which was not leading to much breakthrough. And there was this entire saying that AI is giving rise to IA. Okay, IA stands for intelligent agents. Right, and agent-based computing. Okay, so we'll make a case to agent-based computing for open world computing systems, and what is meant by agency and what is meant by autonomy and so on. Right, and there was a lot of interest in IA computing, that is intelligent agent-based computing. Okay. Now, of course, AI has come back with a bang with neural networks and deep learning and and so on, but what I would still say is that even current day AI, okay, the reason why there's a lot of interest in AI is that it has a lot of commercial potential, the current form of AI, right, with neural networks and so on. But all of them are primarily still useful for, say, supervised learning, that is, you have training data already available, or unsupervised learning where you're just looking at patterns in the data, right? And while we'll say that, I'll give you some examples from what is meant by open world. And the thing is that the moment you take the open world assumption, okay, interpreting the data becomes a completely different problem, right? Why? Because we don't know what we don't know. So we have some data, right? And we can look for patterns in the data, we can look for clusters in the data, whatever we can do, but we don't know what we don't know. We don't know what other data we are missing. right? We have no idea what other data is, right? So in fact, so what my contention is that you might have heard of this thing, right? What is this? Artificial general intelligence, right? If AGI, so AGI is still kind of a, it's not really all that mainstream because primarily there's not much commercial applications over there. But if you really want to study AGI, or if you really want to understand how to create general intelligence, right? I think open world computing and agent-based computing is still very relevant to them. Okay, if you want to create generalized agents, right? And so that's where that's what the backdrop of the whole course is, right? And so even though intelligent agents currently there's not much, you probably won't get a job while studying intelligent agents, but if you want to carry out really deep research in terms of what the nature of intelligence and so on, the idea of autonomy and open world reasoning is still very important in agents. Okay. So any questions so far? Nothing? Nothing at all. Clear till now? Okay. So let us move forward, and so I'll broadly talk about how the course is structured. So broadly, there are 3 modules. So the first module today, what we'll do is classical theory of computation, right? What are the how we got through, Turing machines, uncomputability, all kinds of classical model. The second session will look at the open world problem. That is, how do we characterize the open world problem, right? We don't know what we don't know is one thing, but what are the other things? What are the implications, okay, of saying we have an open world, right? And what if we suddenly open the Turing machine or open the world in which a Turing machine operates, right? And the third session will look at multi-agent computing, okay? So multi-agent systems, okay, which is basically a system of agents are working in an open world. Okay, so I'll define the term agents in a while. Okay, so autonomous agents. Okay, and what happens when a system of agents are pursuing their, self-interest, so to speak. Okay, and computing or interacting with one another, or more importantly, interfering with one another. That is, when every agent is performing its computation, it is not only getting something for itself, but it's also interfering with other agents. That this interference may be either positive or negative for the overall sense. So this is why the whole idea of multi-agent systems becomes important, right? What happens when there is a system of multiple agents that are coming together, and how do we start reasoning about those agents, right? And how do we start building systems around those agents? What is the basis on which we say that, okay, this multi-agent system is correct, or this is incorrect, or so? Okay, so this is the last third module that we'll work on. Okay, I'll also, if time permits, introduce some of the multi-agent solutions that we have created for some different kinds of problems. One is a grid computing problem, one is a spectrum allocation problem, all kinds of different problems where all of which we'll see are open world problems, right? And we'll see how the multi-agent paradigm, okay, is working behind this. Okay, good. So shall we start with module 1? Fine. So all of you are convinced about the open world problem. Okay, so what is the open world problem? In one line, we don't know what we don't know, right? It's very simple. So very simple to understand the open world problem, right? And now how do we deal with an open world problem where we don't know what we don't know, right? And so that's so let us start with some mathematics, okay? And let's start with the most favorite topic of all theoretical scientists, which is set theory, right? And let us try and see how we can build models of computing using set theory, and why set theory is so important. Okay, why a lot of what we understand as computing has got to do with set theory. Okay, so set theory, as we know today, started in the late 19th century by this guy called Gottlob Frege. Okay, so Gottlob Frege's set theory is what is now called as the naive set theory. Okay, and then there are later versions of set theory and so on. Okay, so what is a set? It's a collection of something, right? And so a set theory is the study of collections of something. Okay, and how is collections related to computation or systems, right? So this is what how is. So of course I can write a set like this. How do you write different sets? Let's say A equal to say 2, 3, 7, 11, so on. Okay, so you can write a set of elements. So when I say a set, so this is the set, and these are what are called as elements of the set. Okay, and of course, what can be elements of a set? Just about anything, right? So so can I say this is a set? Yeah. So can I say something A equal to set of all x such that x is a prime number? This is a set, right? And so, or I can say then B equal to set of all y such that you know y is a prime number and y is less than 100. Okay, both are sets. Okay, then can I write something, say C equal to, is this a set? Why? What are the elements of C? The sets A and B. Okay, a set can also contain another set as an element. Okay, what is the difference between a set being an element of a set? So let us say I have you know this thing, right? B is a, is this correct? What is this? So and I'll say B. So what's the difference between the two? Yeah, B is an element of set C, while B is a subset of A. Okay, so you know the difference between a set being an element of a set and a set being a subset of a set. Okay, so what is the difference? When B is a subset of a set, B, there is no B in this. There is no term B anywhere in this, right? And so while the term B here is part of this set. Okay, so there are lots of such sets like this. Can I have a set like this? C equal to what does this set do? A set can be an element of a set, right? And so what is this set saying? C is a set which contains A, B and C. Is there something strange in this? Okay, let's say, no, when I redefine C, this definition is gone. So think of it like a variable. Okay, this variable I assigned like this. Now I reassign the variable. So the earlier assignment is gone. Okay, so we don't have to think of it like this. So we just have the definition of A and definition of B. Okay, now so what is strange about the third set? This definition of C. You see something strange, right? What is strange about this? Yeah, so C is an element of itself, right? So C is a set which contains itself. So what happens with this? We have, so suppose I want to expand this. I'll say this contains A contains so many things, and B contains so many things, and then C contains what? A, B and C, right? And then if I expand all of this, again I'll get this thing. right? And so what happens to such a definition? Now it never ends, right? So you can keep on expanding C forever. Okay, so C is an element of C, that's an element of C, that's an element of C, and it never ends. Okay, so where will you stop? Where will you stop this? Unfolding of a definition, so that I can say, okay, now this is the definition of C. So we'll come back to this question in a while. Okay, this is this is important to understand. So have you got the problem? So a set is a collection of elements. Okay, and it can have lots of there can be different ways in which you can represent elements. Sets can be members of sets. Okay. Now the problem only comes in: is a set a member of itself? Okay. Can a set be a member of itself? Okay. So that's where the problem comes, right? We don't really know. Okay, whether should we have a set a member of itself or not, and so on. Okay. So let's talk about set theory a bit more. Okay. What about suppose I say n equal to is this a set? You thought you had learned set theory in 5th standard, right? So, but now suddenly you're getting all kinds of questions. So, is this a set? What's the problem here? Some elements are getting repeated. Okay, so again, so classical set theory basically says. So we said set is a collection of elements. Okay. Now we are going to refine it a bit further and say no. Set is a collection of element types. Okay. So we say, see, this two and this two are the same. When we represent, when this two just simply means the number 2. Okay. So and the number 5 is the same. Okay. Regardless of whether you say the number or I say the number, it's the same number 5. Right. And so we say no, this is not really set. In fact, this is what is called as a bag, or also called as a multi-set. Right. So we don't treat them as conventionally as sets. We want only element types to be here. Okay. So we say no. The set form of n would be 1, 2, 3, 4, 5. Right. And and this is again in classical set theory. We come to this. What about I have some other p equal to another set. Is this a set? What is this a set of? I get to confuse all my students like this, with we all think we have learned set theory. So is this a set? It's a set of some numbers and a cow. I mean, something seems to be wrong, right? I mean, there are some numbers 1, 2, 3, 4, 5, 6, but suddenly there's something called cow inside here, right? So, so we don't really know what the set is about, right? So now again, mathematicians have argued whether a set should have a criteria, okay, for an element to be a member of it. So I can say, these are all the set of numbers. Integers from 1 to 7. So I say this thing, okay. But suddenly somebody says, thoda adjust kar lo and put a cow also inside this, right? So there's no criteria for the set, right? And so basically, then again, set theory came back and said, no. I mean, all of these, just about any elements can't be a set. In fact, the elements that belong to a set has to have something in common. Okay. If you can find something in common between this, then I'll consider it as a set. Okay. If you can find what is common between cow and 1 to 7, right? I can consider it as a set. Okay. So that means there has to be the set has to be about something. There has to be an aboutness of the set. Okay. So in fact, the way we write a set today is like this. Okay. So what does this mean? So we write a set as a set of elements such that a property or a predicate holds for the set of elements. So P of X means a predicate. Okay, so some kind of so what is a predicate? A predicate is a statement that is either true or false, right? So when we say that a predicate holds, it means that it is true for X. Okay. So for example, I can say something like this: S equal to a set of all X such that X is a member of the set of integers. Okay, and I'll say X. Okay. So what is this set? The set of even numbers, positive or negative, even negative even numbers, right? I just said Z. So, so what is the predicate here? The predicate here is this. Okay, so P of X equal to, I can say X belongs to Z, and say mod of X is 0 is true, right? Both of them are true. So this is the predicate that represents the set. Okay, and the predicate has to be true for the set to be true. So are we all in the same page here? So where did we come to for set theory now? So we said set is a collection of elements. Okay, but it's not just a collection of elements; it's a collection of element types. Okay. We are not an element instance. In fact, each element should be neatly distinct from other elements. Okay. Second, a set is a collection of elements that share a common property, a common predicate. Right. So there is something common or some property that is common across all of these, and then we form the set. Okay. And sets can be members of themselves, and they can, or whether they can be members of themselves, we'll come to that. Sets can be members of other sets, and so on. Right? Fine. Any questions so far? So the reason set theory has got so much of traction or so much of interest in the early 20th century. So we'll talk about connotations of problem solving in a while. Okay? There were some mathematicians like David Hilbert, right, who are sometimes called the universal set theorists. Okay, they basically said that all of mathematics, right, can be represented as set theory. Everything in mathematics, right? In fact, have you heard of the term Hilbert Numbers? Have you come across the term at all, Hilbert Numbers? So Hilbert Numbers, so you can go search the web now that you've heard of the term. Okay, so David Hilbert came out with a complete set theoretic representation of all numbers. See, where does mathematics start, or how did mathematics start, right? Arguably, mathematics started with number theory, right? So we started with counting, we started with quantifying, we started with adding, subtracting, and so on, right? And and then he said, okay, let us go to the foundations of mathematics, and I'll represent all of mathematics using set theory, right? So Hilbert numbers basically look like this. 0 is the null set, okay, and 1 is a set that contains 0, which is basically a set containing the null set. Okay, 2 is a set that contains 0 and 1, which is the set containing null set and the set containing the null set again. Okay, so something like this. Okay. And similarly, 3 equal to 0, 1, 2, which is what? So 0 is the null set. This is a set containing the null set. Okay, and this is what? A set containing the null set and 0 and 1. I'm losing track of. Okay, braces. So everything was built from nothing. Okay, everything was built from null sets. Okay, and then he came out with a set of set theoretic operations. Okay, how do you perform 0 plus 1? How do you perform 1 plus 2 and so on? All of set theoretic operations, plus all of arithmetic operations, plus, minus, multiplication can be written as a series of additions, right? So into can be written as a set of plus and so on. Okay, all of these were reinvented using set theory. Okay, using set theoretic constructs like what union, intersection, set difference, all kinds of and he showed that all of basic arithmetic can be recreated using set theory, and in fact the whole of mathematics can be recreated using set theory, right? And so that was the big dream of David Hilbert, right? And a lot of people shared his dream, and in fact mathematicians still have a tradition. Even in 1999, the tradition was followed. So at the end of each century, they have there is something called as the ICM, the International Congress of Mathematicians, where some of the mathematicians come forth and put forth some of the open problems in mathematics. Okay, so these are the next century's problems, okay, for mathematicians to solve. And one of the problems in the 20th century, that is 1900 ICM, okay, was provided by David Hilbert, which had got to do with the universality of set theory. Okay, so I said, I can do all of basic arithmetic using set theory, but can I do all of mathematics using set theory, right? So we'll come to this question: what is meant by doing all of mathematics using set theory, right? So let me pause for a while. Let me try and get some questions. So are you all firstly awake? Okay. So second, any questions so far? So are you all convinced about the set theory part, why we are starting this, and the universality of set theory, right? And coming to this. Okay. So it's a complex problem, right? Lots of things are coming together. So I want to weave a story, but a story has to have a particular pathway. So I have to take you through a pathway, but I need to come back and ensure that now you're seeing the complete picture. Okay, so all of the things that I've talked about has a reason for now. Okay, the sets belonging to a set and set, the universality of set theory and so on. Okay, so primarily the problem that David Hilbert gave, okay, in the turn of the 20th century. So this problem is what is called as the who can read this for the first time without Entscheidung's problem. So Entscheidung's problem, Entscheidung in German means decision. Okay. So what is the decision problem? So primarily what David Hilbert said is, regardless of what mathematical problem you have, you can represent it as a set. Okay, as a set of the form. So how did we write sets currently? S is a set of. Okay. So regardless of what mathematical problem you have, you can write it like a set like this. Okay. S is a set of X such that P of X holds. Okay. Now the question is, can you represent this P of X as a set or as a set theoretic constant? So can you represent this? What is P of X? P of X is a predicate or a property. Okay, can you represent any property, okay, as a set? Okay, so this is what David Hilbert. So let us try and see why he said this. Okay, so let us look at some connotations of problem solving. Okay, so when you say when you say you perform, you write an algorithm, right, or you perform some computation using a computer and so on. What is it that you're doing mathematically, in the mathematical sense? What are some examples of algorithms that you've written? Adding two numbers, right? Or finding the max of something? What are some algorithms basically? What is the square root of some number? What is the square of a number? Right? So let's take some some problem like this. Okay, so what is the square of a number? So you can are you all convinced that this is a algorithmic problem, mathematical problem to solve. Okay, so I give a number and I get a square of that number, right? So I give you 2, I get 4. Okay, I give you 3, I get 9. Okay, I give you something else, let's say 2.5, and I get 6.25. Okay, or I'll get -4 and I get 16, whatever, right? So what is the generic notion of this problem? What is this looking like? So you see, this basically can be written like this, right? So, right? So there is a what is this, by the way? Function. Okay, you know what a function is, a mapping relation, right? So every problem that we solve using computers, right, can be written like a function. Okay, a function has a this is what is called as a problem domain. Okay, or this is the range of the solution domain. Right? So there is a domain of the set of all problems, and we have to map a problem to a solution. Okay, and that the logic of the mapping is in the algorithm, is the problem that we are solving. Okay, so for example, I give 2, it gets mapped to 4, 3 gets mapped to 9, right, and -4 gets mapped to 16, and so on. Okay, so you see, just about any problem solving is basically like this. You have a problem domain, you have a solution domain, you compute a map. Okay, so this problem, this solution, this problem, this solution. Okay, so now how can you represent this as a set? Okay, now for example, you can say that instead of 2 maps to 4, 3 maps to 9, okay, I can basically write this as tuples, right? So I can say 2, 4, and 3, 9, and 2.5, 6.5, and so on. Right? So I can write this as a set of tuples or pairs, saying if this is the input, this is the output. This is the input, this is the output. Right? So I can write this even further, right? Given any problem, so let us say you want to compute the GCD of 2 numbers, right? So how do you write this as a function? So GCD is a function. Is a function from what to what? From what is your input domain, or what's your problem domain? Set of numbers, or the simplest form, 2 numbers. Okay, so how do you represent 2 numbers? A cross product of this thing, right? So I say a set of 2 integers. I'll just write it z plus as set of 2 positive integers to set of positive integers, right? And so the thing is, so how will element of this function look like? So it will look like a pair where the first element is already a pair, right? So I can say something like 8, 16, and I say, or 8, 20, and I say 4. Is that? Okay, so this is a valid element of this set. Right? Now what have we done? We have reduced a function to a set. Okay, so I can say this is a valid element. Okay, and for example, if the set, for the set F, okay, or I'll call this SQR, right? For the set SQR, okay, is a set of all elements X such that, okay, X is a member of what? X is a member of real times real, okay, and X has some property. Okay, so for example, real times real, where X is of the form y comma x or y comma z. How do I erase this thing? So let me first write it like this. So I can say SQR is a set of the form x comma y. such that x is in real, y is in real, and y equal to x square. Right, now this is my predicate, this is my set. Right. Now what is it I have done? I have reduced the function to a set. Right, and so this is basically the idea behind the Entscheidungs problem. Right, you take any mathematical problem, okay? Basically, it's a function, right? And you can reduce a function to a set like this, okay? Where you just check for a property, and if the property holds, then this is a member of that set. Otherwise, it's not a member of the set. Right? So, got the idea? Yeah.
So we have to indicate this operation in terms of set of I think that square is not a set.
Yeah. So that's a property. So we don't know how to represent this in set, right? And so that's the. You're right that ultimately, if Entscheidungs problem is solved, then each of these will be reduced to a set theory operation. So right now I'm representing it as a property. Right, and so this is the question that the Entscheidungs problem. Can we reduce all of this currently to set theories? Right, and right. So good question. So have you got the idea that this is the problem? Okay, that we can reduce it to a set, but we got it to this level. So what Hilbert's problem is, can we reduce it all the way to set theory? Right, all the way to set theory, complete. Y equal to x square. Can it come down to, he already had created numbers using sets, and all of this can be reduced to set theory, right? And so that's the question. That was the Entscheidungs problem, right? And in fact, what we can do is we can reduce it even further, right? So we can rather than treating a problem as a function, we can treat it as a decision problem, right? That is, we take an element and then we decide whether this element belongs to the set or not, right? So what is the decision problem now? That is, I take the set of all elements from R to R, set of all pairs of R and R, and then I map them to either yes or no. Right, now this is the decision problem of, so I'll call decision problem for square root. Right? So I take the set of all elements from set of all ordered pairs formed by a pair of real numbers, and then ask whether this belongs to the set or not. And in fact, we'll go one step further. So are you all clear now? That is why we reduced this to a set, and how we can reduce this to a set, and how we can reduce this to a decision problem at its very core. Right? So in fact, there's also one more thing that one more terminology I'd like to give before we proceed further. The idea of what is called as the language. Right. So if you see now what we saw earlier, let us say the square root problem or the GCD problem or whatever, right? And so what was the square root problem looking like? So we had a domain set of real numbers, okay, and the square root problem or the square problem is actually an algebra over real numbers. Okay, so what is an algebra? So an algebra is something that takes something from a domain and maps it back to the domain, right? It's basically doing something on the domain, right? And, so how many elements does it take? It takes one element and computes the square. So primarily it takes two elements, right? So let's say it takes R1 and maps it to R2, right? So it takes two elements. Okay. So if you see the square, the problem called square, okay, is essentially, so I'll call this, okay, the set theoretic problem of square, okay, is essentially a subset of what we may call as R square. Okay, so what is R square? R cross R, right? So R square is basically, okay. So what is say R to the n? It is basically R times, okay, so n number of times like this, right? And what is the most generic way in which a problem can be reduced to a set? Okay, so the most generic way, so square is a subset of R square and so on. Any arbitrary problem, okay, can usually be represented as a subset of, so if my domain is called sigma, okay, it need not just be R, right? It need not just be real numbers, it can be any domain, okay. So let's just represent the domain as sigma. We just say it's a subset of sigma star. Okay, so what is sigma star? Sigma star is basically what? Sigma to 0 union sigma to 1 forever, right? That is, it is the set of all strings you can generate from elements of a given set. Okay, what is sigma to the 0? It's basically the null string. Okay, it's not the null set, but the null string. Okay, sigma to the 1 is the set of all one element strings you can make from elements of sigma. Okay, sigma square is the set of all two element strings you can make from sigma. So okay, and so on. So sigma star is the set of all any element strings that you can represent from. Okay. So what we did currently is, now we said every problem is a function, every function is a set, okay, and every set is basically a set of strings, or every problem can be represented as a set of strings or something. Okay, so this is what we call as a language, formal language. Okay, so what do we mean by a formal language? It's simply a set of strings from a given domain. Okay, and the domain is called as the so the sigma is basically called as the alphabet. Okay, so the reason why I'm introducing this terminology is that David Hilbert and others came from number theory. Okay, but then there were people, others like Noam Chomsky and a lot of other people who were working on language technologies. Okay, and then they also came to the same foundations. Okay, from a completely different, they were taking a completely different problem, and they came back to the same foundations. Everything is a set, right? And a set is a language, and this is where this terminology comes from: language, strings, and so on. While mathematicians were using things like Cartesian product, n-dimensional tuple, right? But an n-dimensional tuple and an n-length string is basically the same, right? From a set of from an alphabet, from a set of elements. Fine. So this is how so many different fields came together and said, okay, everything is a set. Okay. Only problem is the Entscheidungs problem. Okay. If we somehow solve this Entscheidungs problem, that is, if we can somehow high-end mathematics can come together and then say that no matter what is the P of X, okay, no matter how I represent the P of X in a set, okay, I can reduce the P of X to a set in set theoretic constraints, right? And then I'm done. Whole of mathematics is just set theory. Okay, fine. Got the idea? It's a great new concept, right? I mean, it's you can now we can have a mathematics machine. Okay, if we can create a machine that does set theory. Now, set theory will be the basis of computers, set theory will be the basis of AI, set theory will be the basis of everything, right? All that we need is the Entscheidungs problem to be solved, fine? So, so this is where we are at the turn of the 20th century. So imagine yourself at the turn of the 20th century, okay? And this was the excitement among all mathematicians, right? And fine. Any questions so far? Yeah, an alphabet is simply the vocabulary or the set of all elements from which we build strings. Alphabet is a set. So, alphabet, the English alphabet, for example, comprises of 26 letters, right? And the binary alphabet comprises of 2 digits, that is 0 and 1. Okay. The decimal alphabet comprises of 10 digits, okay, 0 to 9.
Can the alphabet be a set 0, 1, another set?
Yeah, that will again come back to this. So currently we are saying alphabet is a set of elements. Maybe they are sets, that is all of them can be reduced to sets or not, we don't know. But at some level you can think of them as a set and some elements. Right? So that's the idea of an alphabet. Yeah.
So, but is this like actually as powerful as you look at it? Because if the predicate can be as like something as huge as actually defining the logic, mapping via propositional logic. So like
exactly. Yeah.
Boil down to like actually just finding the function itself.
Yeah. So that's the question. The predicate can be arbitrarily complex. Okay. And the question is whether you can reduce all of them to set theory. Right, all of them to set theoretic constraints. That is union, intersection, set difference, all kinds of okay, regardless of what the predicate is. Okay, so this is where, in fact, I'll just come to Russell in a while. So we'll see. Russell actually tried to do that with Principia Mathematica. So if you go to our library, we actually have the actual versions of Principia Mathematica, the principles of mathematics, right? And there are 3 big volumes. Each volume is this big, and he actually tried to do everything, with set theory and so on. Okay, and Russell was actually a big believer in universal set theory, that we can actually reduce everything to set theory. Okay, but okay, let us try and get some issues with it. Okay, so now the story continues. So Georg Cantor, he was another set theorist. I'll come back to him again in a way. Georg Cantor tried to say, okay, let us try and define everything by a set. Okay, this is a set of this, this is a set of this, and then let us say that I have defined a set, okay, which is the set of all sets. If everything is a set, then I can have a set of all sets, right? Now, what happens to the set of all sets? So what does it mean? H is a set of all H such that H is a set, right? And now, do you see any problems with defining the set of all sets?
Actually, it will become a member.
Yeah. Now the question is H a member of itself? Is H a set of all sets, including H, right? And now one more thing. So this is a question: is H a member of itself? Okay. Another question is, which drove, in fact, Georg Cantor actually died in a mental asylum. Okay, I can tell you why. Okay, we'll see some of the things later on. Okay, so another. Before we go to the next thing, see, let us say I have a set A equal to. Okay, what is this? The power set of A. What is the power set of A? The set of all subsets of A, right? And so, what is this thing? Why is it called 2 power A? Yeah, in fact, you can see that for any finite set, okay, the cardinality of the power set is exactly 2 to the cardinality of the set. Okay, so how much will be the cardinality here? You have the null set, then you have 1, 2, 3, 4, right? All singleton sets. Then you have 1, 2, right? 1, 3, 1, 4, then 2, 3, 4, 3, 4, right? All 2 element sets, then 3 element sets, and so on, right? So totally you'll get exactly 16 subsets in this thing. Okay. Now, and you can see that the cardinality of the power set is definitely bigger than the cardinality of the set. Okay. In fact, it's exponentially bigger for finite sets, right? So now the first question is, if H is a set of all sets, okay, is H a member of itself? Okay. And what happens to 2 power H? Right, now what happens to 2 power H? That is the set of all power sets of the set of all sets, right? Is it going to be in H or is it not going to be in H?
But cardinality is defined only in the case of finite sets.
Okay, we'll come to that. Hold on to that thought. Is cardinality defined only in set of finite sets? In fact, the reason infinities become important is because of cardinality, right? So I'll come back to that in a while. In fact, the whole of uncomputability is based on cardinality of infinite sets. Right? So what happens to 2 power h? We don't know. Again, there's a question, right? And so this really vexed people a lot. How can we get everything down? So then Bertrand Russell, he was another British mathematician who was a contemporary of A.K. Ramanujam and others, right, and Hardy and Cambridge. So he said, see, this entire problem is coming because we are making sets a member of itself, right, and that's why we are getting all kinds of vexed problems, right? So let us define the notion of a well-behaved set. Okay. So what is a well-behaved set? A well-behaved set is the set of all sets X such that X is not a member of itself. Okay. So well-behaved set is where I don't contain myself. I don't start eating myself. Fine. So let's take the set of all sets which can contain other sets, but you don't eat yourself. You can eat others. Okay, so that's the you just don't eat yourself, kind of. Okay. Now this is where it came. Now what is the problem? Now the question is X a member of itself? Is X well behaved? Okay, I said a well-behaved set is something which is a set of all sets that don't contain themselves. So the set of all well-behaved sets, is it a well-behaved set? What do you think is the answer? Yeah, so suppose I say that X is a member of itself. Okay, what does this mean? That means that X is not well-behaved. Right? That means that X should not be a member of itself. Okay? And if X is not a member of itself, what does it mean? It is well behaved. Therefore, it should be member of itself. Okay? And it means it should not be a member of itself. Right? And it keeps going on and on, right? And so if X is well behaved, then it's not well behaved. Then if it's not well behaved, then it is well behaved. So, right? And, so this is the famous Russell's paradox. Right? So in fact, this was one of the first big blow to the Entscheidungs problem, Hilbert's Entscheidungs problem, right? And which, yeah.
So why can't we just say that a set can't be a member of itself? We just define it like that.
In fact, Russell tried to do that. Okay, how do you define it like that? That is, set can't be a member of itself, right? And what kind of, what does it mean to, say, for example, let us say set can't be a member of itself, okay? But let us say it can contain other sets as members, okay? So let us say X contains Y as members, okay, as a member, while Y in turn contains X as a member. Is that possible? Right? And no, none of them are members of themselves, but still you have a circular membership, right? And so you get into all kinds of questions like this. That it's not enough if we just remove a self loop. You have to remove cycles all over the place, right? And, so this was one of the first blow to Russell's Entscheidungs problem. Now you see that with set theory you can't, even though you can represent numbers, addition, multiplication, whatever, there are problems like this, right? In fact, this is Russell's paradox gives us the difference, helps us understand the difference between a set and a property. Okay. Some of the times I keep asking students, do you know the difference between a set and a property or a predicate? Okay. Many times we get this difference with the problem. Okay, so what is the property here? the property here, so in this, so you can write this as a set like this, right? X, P of X, right? What is the P of X here? How do you write P of X? I've written it already. X is not a member of itself, right? So this is P of X, okay? Now this property can exist. X is not a member of itself is not a problem. The property can exist, okay? So I can say, for example, A equal to, okay? So is P of A true? So what is a property? Property is either true or false, right? So is P of A true? Yeah, it is true, right? And so P of A returns true, right? And I say B equal to A comma B, like this. So I'll say what P of B? False. So the property can exist, not an issue, right? But the set that represents this property cannot exist. Can you see the difference between the two? That is, a property is simply a check, okay? So now you see how it gave a blow to Einstein's problem, right? So what was, I think one of you asked the question over there, right? That why don't you represent the property here, right? Where did that go? Yeah, why don't you represent this in terms of sets, right? So why don't you represent, so this was a P of X, part of a P of X, right? And why don't you represent P of X as a set? Is it possible at all? Okay. Now here is a counterexample, right? A counterexample which says that this P of X can exist, but the set that represents this P of X cannot exist. Can you see that a particular P of X exists, but the set that represents that property cannot exist? Okay. So the property can exist, but the collection cannot exist. Fine. There are lots of other blows to the Einstein's problem as well. One more is the Gödel's incompleteness problem. So Gödel's incompleteness theorem that also gave a blow to the Einstein's problem. We'll also talk about Turing machines. Okay, the halting problem and so on, the undecidability problem, which was yet another blow to the Einstein's problem. Right? So today we have kind of buried the Einstein's problem. That is, the Einstein's problem cannot be solved. That's the consensus. That of course, because we cannot represent everything using mathematics, or we cannot represent mathematics using mathematics. Right? So that's the thing we have come to, right? And phew. Okay, so questions. So did you get the Russell's paradox problem? So set of all sets and set of all sets cannot contain themselves and so on. Okay. So what did Russell end out? So in fact, this problem bothered him so much that he created 3 big volumes called Principia Mathematica. Right. Trying to say, no, I mean, Bertrand Russell was still believing that Einstein's problem is solvable. That is, we can still solve Einstein's problem, right? And it's only that these are all some minor issues, and we have to get them back. And so, what is Principia Mathematica all about, right? So, he created what is called as axiomatic set theory. Right? Axiomatic set theory, which also created what is called as the theory of types. Right? So what is? I won't go into axiomatic set theory in detail. In fact, there are several variations of axiomatic set theory. Today, there is something called ZF, Zermelo-Fraenkel set theory, which is called, which is considered the axiomatic basis for set theory, right? So while Gottlob Frege and others' notion of set theory is now called the naive set theory, before the axiomatic set theory, right? So naive set theory can contain paradoxes like this, while axiomatic set theory does not contain a paradox. Okay. So what is the axiomatic set theory all about? A set, in axiomatic set theory, every set is defined at a particular level or abstraction level, so to speak, right? And every set is of this form, right? Of course, X P of X, like this, okay? Such that, okay, P of X can be defined in terms of sets, okay, only so far as the set theoretic definition of P of X is some abstraction level below that of S, right? So you can say, for example, I'll say level of S is something, okay, and I'll say level of P of X, okay, it should be strictly less than the abstraction level of S. So basically that's the idea of this thing. That is, everything has to be built from lower level properties, right? You cannot build from the air like this directly. Okay, if you have to have a solid foundation. Okay, you cannot build a upper floor before building the lower floor, right? And so everything has to be built from ground up, and which means that, what does it mean? If I have something like this, that there is something called axioma, that is the ground truth. So every set is grounded in some atomic elements, okay, which cannot be divided further, right? So everything is built from atomic elements, and the atomic elements could be some, the null set or some kind of atomic elements, and then you build everything from ground up, like this, right? And so this is where Russell came up with, and he said, okay, now with this axiomatic set theory, you can still do Entscheidung's problem, and you can still do a lot of mathematics, and but then even that was shown to be not possible. We'll come to that story, what Turing did, right? And so even that Turing said, no, that's even that is not possible. So, okay. So that's quite a bit of theory already. So any questions so far before we change gears a bit? So have you got the idea of what was bothering Russell and why the P of X, what is the Entscheidung's problem really? That is, you take the P of X and reduce it to a set, right? And if you can do that, then all of mathematics can be represented as a set, right? Except that there are problems like well-defined sets, or well-behaved sets, sets that don't contain themselves. Now you can't really reduce them, right? And or in fact, those sets cannot exist at all. Okay, so then you have a axiomatic set theory and so on. But basically, what happened was the axiomatic set theory. Again, what Russell came up with today. One thing it was very good was that it created a theory of types and subtypes. Okay, so you can see that the abstraction level creates a particular notion of a type. Okay, so S is of type this level entity, right? And then there are lower level types. Okay, so higher level types can be built from lower level types. So you can say this P of X is built from lower level Q of X, R of X, whatever, right? And lower level predicates. And these lower level predicates can be built from even more lower level predicates and so on. Okay, and in fact, a lot of programming language constructs today on type theory uses this in terms of how to build theory of types and so on. Okay, but there is a problem. Okay, the problem is that it does not always make sense to say you should always build everything from lower level constructs. Okay, mathematics is not a building, right? When you build a building, it's one thing. Okay, but mathematics is not a building. Okay, self-reference is there all over the place. Okay, so suppose I say that this sentence is talking about something. Okay, now suppose I want to represent this sentence as a set of all the objects that it refers to. Okay, so I say that okay, let's say so this comes from language technologies, right? this sentence is an experiment. Right? Now suppose I have to represent this sentence, right? I'll call this as T. Okay, T equal to this sentence is an experiment. Okay. Now suppose I want to represent T as a set of all objects that are referred to by this sentence. Okay, of all conceptual objects, nouns. Right? What are all the objects that it is referring to? This is referring to an object called experiment. Right? And this is referring to this sentence, which is T itself. Right? And this is a very valid English sentence, right? I mean, there's nothing wrong with this sentence. Okay, this sentence is an experiment, or I am so many years old, or whatever, right? I can talk about myself, right? Or so having self-reference or a set containing itself is not really a problem in itself, right? So take so what I called well-behaved sets that Russell said, okay, is actually in mathematics it's called as well-founded sets. Okay, a well-founded set is a set such that it is not a member of itself. Okay, so Russell basically wanted to create the set of all well-founded sets. Okay, but you can still create a non-well-founded set. Okay, so what is a non-well-founded set? Such where X is a member of a set X such that X is a member of itself. Okay, and let us say I create the set of all non-well-founded sets. Okay, X is the set of all X is the set of all sets such that X is a member of itself. Okay, now does this set exist? So is capital X a member of itself? So set of all non-well-founded sets, okay, which are members of themselves. Is the set of all non-well-founded set a member of itself? What do you think? It is, right? I mean, is there any problem with that? There is no problem. I know there are lots of recursive loops running in your head trying to look for a problem, but there is no problem, right? So X can be a member of itself. A non-well-founded set can be a member of itself. There is no problem, right? And so you see, the problem was not with this, right? The problem was here, well-founded sets, right? And in fact, there is really no reason for a set not to contain itself. Right, and so this is what is called as a non-well-founded set is now what is also called as a hyperset. Right, so the theory of hypersets is now we'll come to why the theory of hyperset, and I'll try and connect the open world computing problem to hypersets and so on. So the whole idea of hypersets is still was completely thrown away by Russell's axiomatic set theory, right? So axiomatic set theory wanted everything to be based on a foundation, which basically meant that you can't have self-references, which are an important element of any kind of intelligence or algorithms. Recursion is a very important element of algorithms, right? And so if you see lots of functional programming, it's completely based on recursion, right? And so recursive definitions are useful, are important, and it kind of throws away all those, right? And so now mathematicians still use hypersets, okay, and it doesn't say that okay you have to reduce everything down to an axiomatic set. What is the problem with non-well-founded sets, by the way? I mean, why did Russell and others throw away and other? What is the problem with non-well-founded sets? The fact that it is not well-founded. right? So it is like saying, somebody was asking the other day, how do I come to IIIT-B? Where is it? And I said, it's right in front of Infosys main gate. How do I come to Infosys main gate? Right in front of IIIT-B. Right? Both are correct answers, right? And so it's and where are both of them? Both are in front of each other, right? Which is fine. Right? So yeah, it's correct. But what is the problem? It's not well founded. Okay, how do I get to either of those? Right? So once you go here, you can go there. Once you go there, you can go here, right? And but how do I go there in the first place, right? And so as long as we can address this, the non-well-foundedness of it's the same problem with recursion, right? Fibonacci numbers, okay? F of n equal to f of n minus 1 plus f of n minus 2, which is fine, except that you should define what is f of 0 and f of 1, right? And beyond that, if you don't define that, it can keep going on and on, right? And so you need to somehow, ground the non-well-founded sets. So if you can ground the non-well-founded sets somehow, then you can actually use the power of non-well-founded sets, okay, to very rich degrees, right? And okay, so I know all of you are fatigued in some way, so but I just want to see how well we can. So any questions? I'd like to. I wanted to actually finish with classical theory of computing so far, but there's still some way to go before we finish the classical theory of computing. So maybe it will stretch into the next session as well. But I think it's important to understand the foundations very well. So clear so far? Okay. Now basically what, so this was with set theory and language theory and so on. While on the other hand, there were people like Alan Turing and others, right? And so they were interested in the problem of computing itself, or algorithms itself, right? And what can we compute or what can't we compute and so on, okay? What do we mean by computing? Okay, how can we reduce everything to a computer? So there were quite a few basic mathematical models for performing computing. The most simplest mathematical model is the finite state machine, or also called the TFA, right? So I hope all of you have studied finite state machines to some extent. So what is a finite state machine? Also called an automaton, right? Deterministic finite automaton. So what is the idea of a finite state machine? And how can we reduce it back to algorithms and so on? Have you studied finite state machines? Can we skip through this very fast so that we can come to theory of computing? Okay. So what is a finite state machine comprised of? So it basically comprises of some set of states. Okay. And some, maybe some loops here and some loops here and so on. Okay. So, so what is the idea here? It is a automaton or a very basic computing machine that can recognize certain kinds of strings. Okay. So what did we do earlier? We said every problem is a function, every function is a set, every set is a language. Ultimately, we reduced every problem to a language, right? And now you can actually solve certain problems, right? So our set of problems, right? So S equal to X given P of X, okay? Now for certain kinds of P of X problems, we can actually solve using finite state machines, right? So how does what is the formal model of a finite state machine? So you have a BFA equal to a set of states, okay, then a set of symbols, which is our alphabet, okay. There's a unique start state, then there's a transition, okay, where S0 is a member of S and delta is what? State times symbol gives state, right? So at a given state, if you read a particular symbol, you go to another state. If you read another symbol, you go to another state, and so on. Okay, so that's the simple. So that means for a particular class of P of x, right? For a particular class of properties like this, we can solve using the finite state machine, right? This class is amazingly big. In fact, it is infinitely big. Okay, we'll see what are the number of problems that are solvable by DFA, right? So this class of problems that can be solved by an automaton, what are they called? Any idea? Right? A regular language. Any language that can be recognized by a finite state machine is called a regular language, right? And this class of machines is amazingly versatile and amazingly rich. In fact, you can solve a lot of problems using just state machines. Okay. In fact, here is one assertion I'm going to make. Okay, I'd like you to either prove it or disprove it in the next class. Okay, every finite language is regular. So what do I mean by that? Every set, which is a set of strings that is finite, that is the set is finite, okay, is regular. That means you can write a automaton to recognize that string. Okay. So can you prove or disprove that in the next class? Say that. So this is an assertion that I'm making. Okay. You can try some more problems. What all you can do with regular. Okay. So here are some exercises you can try for the next class. Okay, which you can solve for yourself. Take a alphabet, binary alphabet. Okay, sigma equal to 0, 1. Okay, that is our standard binary alphabet. And let us see if you can build a state machine which can recognize binary strings, okay, that are even numbers. Can you do that? I mean, I'm sure you would have worked on this, right? So what is the pattern for an even number? Yeah, in a binary arithmetic, an even number ends with 0. What about a string that represents a multiple of 4? Ending with 2 zeros, no problem. Okay. And what about a string that contains odd number of ones? How would you solve this? What is the general idea? You can come out with the actual solution in the next class, but what would be the general idea for this? Yeah, so keep track of how many ones you have received. So initially you have an even number of ones. Okay, as soon as you get a 1, you go to a state that represents an odd number of ones, and as long as you keep getting zeros, you keep being in the state. If you find one more 1, you come back to the state which says you have an even number of zeros. Okay, so you can actually do odd, even, and so on. Okay, and what about things like this? Okay, odd number of ones and even number of zeros. Okay, or odd number of ones or even number of zeros. Okay. You can do a lot of logical operations with this. Okay, so try this out. So whether you can build a state machine to find and or and so on. Okay, and finally, multiple of any arbitrary number. So let me say multiple of 3. Any binary number which is a multiple of 3, can you recognize using a state machine? How would you do that?
Multiple of 3
there is, what is the pattern is, multiple of 2, there is a pattern, it ends with 0. Multiple of 4, there is another pattern, it ends with 2 zeros. What about multiple of 3, multiple of 5? There is no pattern, but can you still recognize this? Try it out. Okay, so in fact you can still do this. Okay, the hint is of course, look at the modulo arithmetic of this thing. So when you divide any number with 3, you can you'll either get a remainder of 0 or 1 or 2, right? Now, if you can represent states for what is the remainder of, so let us say you have read some number n so far, okay, and the next digit you get is 0 or 1, okay. So the next digit you get is b, okay. How do you represent the actual number that you have got till now? So you have read some number n till now, and then you read the next digit, which is b. What is that? So what is the overall number now? In binary form. In binary form, if I've read some binary number which is n, and the next digit I read is b, what is the total? Yeah. So which is basically 2n plus b, right? Now this is the hint. Okay, so whenever you read a number, the overall number you have finally read is 2n plus b, right? And if you have a representation for 2n, whether it is mod 0 or that is the modulo 3, whether it is 0 or 1 or 2, then you can reason what will be 2n plus b, and then you can still write a state machine. So state machines are amazingly versatile, right? And so regular languages which represent state machines are amazingly versatile, okay? But we can actually show that, and in fact, the number of regular languages, like I said, okay, is infinite. You can have an infinite number of regular languages, right? And yet, so there is a difference between something that is infinite and something that is bounded, okay? So what we are saying is the set of all regular languages is infinite, yet it is bounded. What do I mean by that? So what do I mean by something is infinite yet bounded? So let us say you're watching at some point in Earth, right? And you're watching forever like this, right? So how much can you see theoretically? You can see infinitely far away from here, yet you still can't see something behind, right? So that's the analogy behind this thing. That is, you can have an infinite number of strings or languages which are recognized by DFA, but there are still some kinds of P of X which I mentioned right now, which you can probably cannot solve using finite automata, right? Of course, the main well-known thing is counting, right? So what is this set of strings here? A set of strings that have some zeros followed by the same number of ones, right? And so the problem with regular languages is that they can't keep track of how many zeros you have written. Okay, they can only keep track of some properties of the zeros, whether I have read an odd number of zeros, even number of zeros, and so on, but not how many zeros I have written, right? And so that is where there are multiple other models that have come up. So what we'll do is in the next class, that's tomorrow's session, so we'll take up from this point onwards. That is, we'll look at the next set of computing machines like context-free grammars and push-down automata and so on. Then also see where they are bounded, okay, and come up with Turing machines, and then again see how Turing machine in turn connects back to the Entscheidungs problem that we talked about, and how Turing machine again shows that Entscheidungs problem cannot be solved, right? And so that's the classical theory of computation. That's where the theory of computation rests on. Then we'll come back to hypersets that we talked about, which Russell throwed away, right? Using Russell's paradox and so on. And then see none of these use hypertext, right? None of finite automata or context-free grammars or Turing machines, none of them use hypertext. So we'll try to see how we'll bring it back into computing and see what that means, right? So good. So let's stop at this stage.